Hi, everybody. Thanks so much for inviting me, and happy Friday. So I'm going to talk about thinking within Gemini, and I'm going to try and make this talk reasonably accessible. I'm going to build up the motivation for why we invested in thinking, and then I'm going to tell you about how it works and what we're seeing with it. But just a quick note about myself. So I'm a research lead of thinking within Gemini. And previously, I was one of the pre-training leads within Gemini, and before Gemini existed, some of the large language model projects within Google DeepMind. My kind of passion is to just make incredibly intelligent models. I've spent most of my career working on memory and pre-training topics, and in the last 7-8 months, I've been really more focused on the post-training and reinforcement learning side, specifically focusing on thinking. And obviously, creating AGI is one problem, but having consistent screen sharing is also a hard problem too. So I'm very appreciative.
Always something in the way of AGI.
Yeah. In fact, one of the old DeepMind offices in London, there was like a faulty lift, and it would often just occasionally go to it would say it's going to the 32nd floor. There was only 5 floors in the building. And if it did that, it would go up to the top floor and then just get stuck. And actually the only time I met Eric Schmidt, I wasn't expecting him to be in the office. And I got in the elevator and he walked into the elevator. I was like, oh, that's definitely Eric Schmidt. I recognize him. And then I pressed number 5 and it went up to the 32nd floor and then got stuck. And we had a really nice 5 to 10 minute conversation. And our conclusion at the end was we need to solve AGI, and then when we've solved AGI, we need to solve the lift system in the London office. Oh, perfect. Okay.
All right.
So, so I'm going to motivate why we're very excited about thinking with talking about a compute bottleneck, specifically a test time compute bottleneck, which we feel like was truly kind of something in the way of creating models which are generally intelligent. And we're going to motivate from the compute bottleneck why we came up with thinking. We're going to talk a bit pragmatically about what is thinking. I'm sure many of you have used Gemini models and they say thinking and something happens, but we'll talk a bit more about it in detail. And then we're going to say kind of why should you care as developers? And the message of that section will be about capability and steerability. And then I'm just going to kind of talk a little bit about 2.5 Pro. Obviously, I devised these slides before 2.5 Flash launched in part, but this is an incredible model to spotlight because it's our most capable model, and it also uses thinking natively. So firstly, the compute bottleneck. So the message of this section is that intelligence has been bottlenecked by test time compute, and our solution to this is thinking. So traditionally, and by traditionally I mean throughout all kind of large model research time, but certainly until late last year, we would train models to respond immediately to requests. So if you have a question, or if you have an API request, it goes to the model, and the model may be able to read your full question, but essentially it has to respond immediately. It has to start generating its response or generating its answer after one forward pass through a large language model, which is just a neural network. So in this kind of diagram, we have a request going in, the model is able to read it all, but it has one forward pass, we call it, through a neural network, which is here kind of represented with a bunch of rectangles. And this is kind of like an abstract representation of how our artificial neural network looks, where there's multiple layers, there's parallel compute per layer, and then the model has to immediately start responding. Now, we can think of this compute, the compute spent by the model, as test time compute, and this is the compute the model can spend to try and specialize its own intelligence towards the actual question or request that you are giving it. So the amount of compute it can spend at test time, we think, is a bit of a proxy for how much it thinks about your specific request. And in this setup, in the traditional setup, it's one single forward pass of the network. So it's kind of a static quantity. So if your network has 64 layers and it has some kind of width, some dimensionality, there's some amount of parallel computation that can happen per layer, and there's some fixed number of layers, but essentially that is the compute that you have, and there's no changing that depending on the difficulty of your problem. And it's actually kind of remarkable how much can happen within a single forward passive neural network. So the model is able to, recall multiple pieces of information, potentially multiple per layer. It can integrate that information across its layers. It can combine existing knowledge, potentially via its attention mechanism. It can perform intermediate calculations, so it can kind of keep track of intermediate states, explore multiple ideas. It doesn't have to commit to one idea in this kind of abstract representation that it learns to use. And it does all this to arrive at useful response, and kind of large language models have been very useful for people. So it's been kind of pretty good. But, what if you have some requests and, the model is just not smart enough? What do you have at your disposal to apply more test time compute? Well, the simplest thing would be to use a larger model. So, you'll see within Gemini, for example, we have a tier of models, Flashlight, Flash, Pro. These represent increasing size of a base neural network. And, one option you have is I'll pick a specific tier. If it's not really smart enough, I'll try a larger tier. And I'll get some larger amount of inference time compute for my particular problem. And also maybe the larger network also has maybe a slightly larger and more kind of rich knowledge base as well. But that's basically what you have at your disposal. So that's, on some level, it's pretty good. You now have some options. And also, there is some kind of change in order of magnitude that you can play with there for the amount of intelligence you might want for your application. So this is just already is looking out of date, but say like Gemini API prices across a bunch of models that we provide currently. And if you went from the cheapest to the kind of most expensive, there's like a 2 order of magnitude difference in cost. So maybe there's some notion of, okay, I have some varying lever of how much test time compute I can have, and I maybe have up to something like 2 orders of magnitude. But you essentially are committed for any given type of problem to picking the model tier that you want to go with, and then committed to that for all requests. So this is good, but can we do better? People might want to be able to have 3 or 4 or 5 orders of magnitude in intelligence, depending on how challenging their particular tasks are. So maybe 2 orders of magnitude is cool, but 4 or 5 would be even more useful for you. More kind of dynamic intelligence, more adaptive. Also, you might not want to be able to pre-commit to a specific amount of test time compute for a particular query. For all of your queries. You might want some queries to have less test time compute, some queries to have more, because just intrinsically, some queries are easier for the model to handle and some are more complex. And you want this to be dynamic such that you're serving and it just takes care of it. This is essentially encountering the inference time bottleneck. Having one fixed amount of test time compute instead of something which can be much more dynamic and can be adaptive per query. And we're going to talk about our solution, which is thinking within Gemini. So what is thinking? So pragmatically, you may have seen this in the Gemini app. You may have seen it in AI Studio. The model has now got a space where it can emit tokens, which we call thinking tokens, between the request and the response. So we train the model to think. So intuitively, already this makes sense from an intuitive perspective. If you're put on the spot with a question and you have to respond immediately, it's very difficult. If you're given some period of time to dwell on the question, explore alternatives, think about it a bit more deeply, you're more likely to come up with the correct solution. So this is essentially what Gemini thinking is. And if we kind of bring it back to this notion of test time compute, what these thinking tokens allow is for the model to spend many forward passes, which is a proxy for how much test time compute it can spend. It can spend 1 to tens of thousands of forward passes to dwell on the problem before committing to a response. So already we can train a model to adaptively decide how much to think per problem, and it can emit some tokens, and those tokens can be useful. But crucially, we essentially relax the constraint and allow the model to just spend a lot more compute, and it can do a lot of things with that compute in order to kind of be more useful. So I think then the natural question is kind of, how do we train these models to think? How do we actually construct this? Are we maybe putting in some kind of prompt Like, let's think step by step. Are we trying to have some kind of templated structure to what the model should be doing for any given problem? And I think one takeaway is that we try and use a very general training recipe to teach the model to think. So we use reinforcement learning as a very crucial training stage on top of a pre-trained model. So when we're building Gemini models, we pre-train them first by training them to predict the next token over a large corpus of information. And then we train them with reinforcement learning to do two things. One is to try and create responses that maximize human preference, and also to be able to solve actual tasks and get them correct. So we train them, here there's a kind of a notion of a green line and a red line. We train them with positive reinforcement for, say, correct solutions. We train them with negative reinforcement for things which are incorrect. And I think what I can say about thinking is, essentially, we just allow the model space to perform thinking computation as part of a general recipe during reinforcement learning, such that the model starts to learn to use these thinking tokens and this test time compute, crucially, as a mechanism to be more accurate, more helpful, more capable. So instead of placing a lot of kind of human priors on what should happen in thinking, we just let the model learn what to use this thinking tokens for. Now, we were actually kind of amazed at what kind of phenomena started emerging in thinking. This is kind of from last year. This was just like an example of like one of the first times we saw very cool emergent behavior. The model does not want you to see its early thinking process. But essentially, we weren't really sure like what the best way to kind of train these models to think would be. And so we weren't really sure this reinforcement learning approach, which is very general, would be powerful enough to see kind of cool phenomenon. We thought maybe we may need to institute a lot of structure in terms of maybe some kind of branching or error correction. And what we found was, in this example, even just like some kind of simple math problem where there's kind of like a sequence of numbers, you have to predict the next number, and it's kind of like a bit of a mathematical puzzle, really. You're trying to think of what's the underlying function that might satisfy the current numbers and what would be the next number. And, you know, we found in the thought traces, the model is kind of, it has some hunch on what the formula might be, and then it tests it on the current sequence and then decides, actually, no, that doesn't make sense, the formula doesn't hold, and decides to use another approach. So this was like one of these very early things that we felt like was a real aha moment. We felt very excited that the model is like learning some emergent self-correction behavior. And we thought that's pretty cool. And actually, kind of in the last 6 to 8 months that we've been really focused on thinking, we see a lot of very cool emergent behavior of the model, of what it decides to spend its test time compute on. It breaks down problems into components. It explores multiple correct solutions. It drafts kind of components of a larger response, maybe fragments of code. It performs intermediate calculations. If you're kind of maybe doing some kind of information retrieval task on a big financial document, maybe you need to aggregate lots of intermediate values. It decides to spend its kind of thinking tokens on this. And also, it has a pretty nice ability to use tools such as code execution and search in order to kind of ultimately, as a general rule, do what it was trained to do with reinforcement learning, which is give smarter and more accurate responses. So then the next question is, okay, there was this kind of theoretical bottleneck that researchers have come up with around test time compute, and there was a solution they came up with. They're exciting, but you know, why should this matter to me as a developer? And I think there's two specific things where thinking may really apply to you. One is more capable models. I think that one is kind of, I can go into detail, but I think it's kind of intuitive. We're trying to make the model smarter. And the other one is an observation of why maybe even the rate of change of capability changes and is accelerating. So on that note, we can think really about how AI progress has kind of manifested in the last 6 years, especially in terms of paradigms. So although we had pre-training for several decades, since 2019, there's been a real kind of new change in paradigm of pre-training where scaling data and model size has been showing empirically kind of predictable and very useful capability gains. So the pre-training era began. And then the post-training era, or paradigm, should I say, of combining that, so combining a large base language model with like high quality human feedback. This allows us to transform a very powerful large language model into something like a chat agent or more of a instruction-tuned model that can actually do useful stuff. So stacking pre-training and post-training has already given us a lot and creates a lot of the amazing models that we're familiar with today. And we feel like thinking, which is, we feel like this is a new paradigm where scaling this test time compute is leading to an increase in capability in especially reasoning domains and coding domains. And the kind of thing that maybe matters to you is all of these paradigms are still running. And within Google, we are like actively working on all of them, and they all compound. So by scaling all three, we see accelerated progress. We kind of can see that with some kind of math coding, STEM tasks. These are kind of benchmarks that we look at as researchers. We'll talk more about real-world tasks soon, but we can see that there's a lot of challenging tasks that were essentially where the model was kind of like a D grade at, like, say, the math or coding task back in the distant past of December last year. And that was the forefront of AI, really, was around that capability level. Whereas we've seen kind of in the last couple of months, several of these kind of very challenging benchmarks going from kind of like a D grade to a B or an A grade in capability. So introducing thinking, we feel like, is contributing in the large to this kind of jump in capability for a new tier of harder problems. And on the right-hand side, this is a plot of like a few of our kind of staged launches from Gemini. So from our 2.0 Flash launch back in December, then we had a thinking model in December as well. We had an updated thinking model, and now we have a native thinking 2.5 Pro model. And we've just seen kind of a continuous march of progress in very, very hard tasks. But actually, other than just like things are moving fast in terms of time, if we re-parameterize the x-axis and talk about the amount of test time compute these models have, we actually see quite a nice, so the x-axis here is kind of like a log scale in test time compute. And it's like, it's not exactly labeled from like x-axis in detail, but what you can see is really about the trend. There's kind of like a log linear relationship in these models. As we're applying more inference time compute with these successive models, we're seeing better capability. So we're seeing fast progress, and we're also seeing a lot of the source of that fast progress is by giving models more test time compute. Okay, so I talked about capability. What else is interesting? So another is steerability. So we want to empower developers to steer cost versus quality. So I think I mentioned earlier, in the kind of era of a set number of model sizes, you have to really choose your particular model tier and then commit to it for all of the kind of applications that you're going to use it for. It can't necessarily modulate per request. Now, we feel like instead of having kind of a discrete number of points, which you can think of as cost versus quality as a trade-off right now, it would be really nice to be able to have a smooth slider such that you can kind of really modulate the cost to quality that makes sense for your own application. So we feel like thinking can and should allow the user to have a more fine-grained control over cost versus quality. And this led us to steerable thinking budgets, which we actually just launched yesterday with the announcement of 2.5 Flash. So 2.5 Flash, which was launched yesterday, great timing, this Friday's event, so I can talk about it. This one gives us a new feature where within the API and also within AI Studio via the user interface, you can actually specify a smooth slider of how much the model should be thinking in terms of kind of a token budget. So here are two kind of tasks where one is like kind of a sciencey task, one is a coding task, where you can see like what would happen if you choose, like you slide along this kind of axis into some particular points of, say, cost versus quality. And in this case, on the right-hand side, say live code bench V5, these are not especially challenging coding problems. So it's kind of interesting. In this one, there's like a natural kind of, if you want the best possible performance, you would slide up to 16K. It's not showing actually additional benefit from going up to 24K. In this other more kind of like tricky PhD level science question task on the left-hand side, you can see like just sliding it up is continuing to give you better performance, but it also incurs more costs because the model will emit more tokens when it's generating its response. Another thing that we want, other than very like steerable thinking budgets, is just amazing intelligence to dollar. So we want Gemini models to be really at the forefront of quality to cost. And this is just like a figure that someone generated on X that I thought was nicer than our official figures, but it's kind of fun. You can see, yeah, on the x-axis, it's kind of the API cost, and on the y-axis, this is actually a particular sciencey task. You can see Gemini models like right on the Pareto frontier of this cost to intelligence. And we feel like this is super important because if you're going to actually use these models and you're going to have applications that are really trying to generate a lot of value, then you need these things to be as cheap and cost effective, but as powerful as possible. Okay, so I've talked a little bit about why, from a research perspective, we were motivated to work on thinking, what it is very kind of functionally, what it can kind of bring to as a developer. I'll just talk a bit on 2.5 Pro. So this is a recent model we launched only a couple of weeks ago. It's our most intelligent AI model, has very strong performance, not only, so I've talked a little bit in this research talk of kind of more academic benchmarks, but also held out real world benchmarks that we don't generate and we don't run ourselves. One is Ada Polyglot. This is kind of a real world coding benchmark where you have to make actual code edits on a code base. This was absolutely top of the leaderboard and just pure quality. Now that OpenAI have launched O3, this is also doing very strong. But what you can see with 2.5 Pro is it's incredibly accurate and strong in this benchmark so far. And it's also incredibly inexpensive. So the green bars are percent correct, blue bars are cost. So it's kind of a really nice point in terms of that trade-off. There's also kind of like agentic coding. Devin have an agentic coding leaderboard. 2.5 Pro is currently the most strong model in this space, which is really cool. There are other held out evals, for example, Scale run a bunch of held out evals looking at various different qualities such as tool use, instruction following, and kind of like a knowledge seeking, difficult question answering task, humanities last exam. 2.5 Pro is really, really strong on that. And also we saw in some domains which require a lot of reasoning, like very challenging math. So the USA Math Olympiad, in the history of kind of these models, none of them have really gone beyond like 5% accuracy. They can't really solve this like kind of difficulty level of math tasks. And we're starting to see like an emergence with 2.5 Pro of like models which can now start to compete almost like at national level math capability. And this is important because ultimately we want these models to be able to bridge the gap up to the kind of intelligence and expertise of kind of a world-class researcher, such that it can eventually use these models to really push the forefront of human knowledge and do useful scientific endeavor. This is like a goal that has been very aligned with DeepMind throughout its history, not only building intelligence, but also having it create a lot of economic, but also scientific impact. And ultimately, you know, when all is said and done, you really want this model to be able to play Pokemon very well. And, you know, there's like, this is just independently run. People love like taking these models like Claude and 2.5 Pro, and we don't really have any involvement in this, but it's kind of fun to watch. There's like a Twitch stream where you can see 2.5 Pro playing Pokemon. We don't add any, needless to say, we don't add Pokemon data into our training set. Yeah, so it's still going. And okay, so I talked a lot about stuff. Actually, Paige is going to give really cool demos that are live, but you know, some notions of what does thinking look like in practice if you haven't used it. So in this question, in this kind of request, it was about generating some Colab data visualization code. It first needed to generate some data, and then in this case, it generated a load of code that we put into Colab and run, and created a kind of data science visualization that was like an interactive thing that you could play with, which is cool. And so hooray. And then, there we go. In another example, this isn't a video, but I thought it was really cool. Some people at DeepMind were just feeding in the paper of DQN, which is kind of the original research breakthrough from DeepMind back in 2013. I actually went to the research conference where this was presented. Coincidentally, I wasn't at DeepMind at the time. And it's about training a simple reinforcement learning agent to play Atari. In this case, it was a kind of a vibe coding session to get the model to generate a training code base that would create DQN and also create a simple Atari environment, and then train a model, and then create some visualizations of the model playing it. It's kind of a very complex setup. I should note, there are instances of people writing such code bases on the internet, so this is a truly held out problem, but it's still quite remarkable. You can essentially speed run like a quite complex research idea with I think this was like 4 or 5 interactions from the model, and build not only a training code base, but like a whole visualization suite. And these kind of things took many researchers many, many months back in early DeepMind days. So that's very cool. And I have another kind of demo of also, because real world code is very, oh no, this one's not real world code. Obviously also, why did we call it thinking? We could have called this reasoning. And so when we were starting this, we really felt like we want thinking to benefit creative tasks and not just kind of logical reasoning tasks. So poetry, this is like a complex poem form villanelle. If you're into your poetry, you may be aware of it. I just thought, can the model generate a villanelle poem about Jeff Dean? And it's kind of fun seeing its thoughts. It kind of, it decides about like a bunch of different themes that it might want to talk about, like Big Table or some of Jeff Dean's like early career highlights, and then thinks about all the different rhyming structure, and then eventually comes up with the villanelle. So it can actually remarkably transfer, not just from very like reasoning heavy coding and math tasks to creative tasks, which we wanted to see. And also, ultimately, other than kind of simple data science kind of applications or, oh no, we're doing poems again. Yeah, sorry, I don't know how to do videos and slide. Also, I think this one, I may skip into a bit, but it can also kind of one-shot. This is another thing we were very excited to see from 2.5 Pro, like one-shotting. So this is kind of like an interactive web app that's a cake design visualizer. Now, ultimately, the model has to really think deeply on this one. And I was originally thinking of demoing this and then walking over to this amazing marble fireplace and remarking on the craftsmanship that must have gone into that. And also remarking there was a lot of amazing craftsmanship that went into these models behind the scenes. You play with them, they're kind of fun, or they're quirky, or they have some bugs, and it feels like a very simple experience, but behind the scenes, there's kind of like an amazing amount of kind of labor of love that goes into making these things work well. But yeah, crucially, this model spends a lot of time thinking. It writes a lot of code. I'm going to skip through it, just and then it kind of makes what is like a somewhat non-trivial web app with quite a few different types of interactions. It's kind of like supposed to emulate, I think, if you are maybe making some kind of cake design online site or something, and you want to design your cake, and then it's going to be a pretty expensive cake. Maybe you're going to get married. Could be exciting, but you want your AI to generate the cake. But then you realize also you want, to make some kind of, you want to make this not just like a 3-tier cake all the time, and then it goes away and it spends a lot of time and it writes several hundred lines more code. And long story short, it has to think deeply and it has to generate quite a lot of code, but ultimately it can do quite complex things in a one-shot. And we're so spoiled these days that waiting a minute for a model seems like the hardest thing ever, whereas once upon a time we had to sit down and spend like 3 weeks adding the variable number of cake tier functionality into our web app. So it's, so ultimately we train these things to think. We often focus on benchmarks and ways of measuring progress in terms of reasoning, but we like to see transfer and capability in real world tasks, creative tasks. And ultimately we're very excited 2.5 Pro is out, and now 2.5 Flash, which is also a native thinking model and is faster and more cost effective, is out, and that's what you're all going to be playing with. And yeah, so then what's next? We are excited about more capable models. We're not stopping now. Gemini will be better and better over time. Especially, we're interested in making thinking, as we mentioned, steerable. This is just the start into trying to get the model to really apply the relevant amount of thinking that's right for your task. We want to make that a better experience for developers. We want also thinking to be more and more efficient. If you interact with models, you may see they kind of overthink. This adds unnecessary latency. If you could kind of trust it in an automatic mode to think a very reasonable amount of time, then we feel like this would be a better and better experience. And maybe in automatic mode, then you can just kind of trust it to do the right thing. 2.5 Flash is a step in that direction. It has much better thinking efficiency than 2.5 Pro, which is a bit more prone to overthinking. But we really want to make this better. So ideally, really in future, thinking should be a thing that you almost don't have to consider. You just are going to get better capability. It's going to be steerable in case you want to interact with it, but it hopefully should work for you. And that's what we want. So that was it. Thank you, everyone.